Tell me, young one, how would one design the software for an automated teller machine?
I've given this some thought, Master, and here's my solution.
Grasshopper, did I not tell you back in episode 7 that the architecture of an application should be based on its use cases? What are those use cases, young novice?
I've made a list of them, Master.
Well done, Grasshopper. Of course, the use cases for an automated teller machine are well known. There must be some way to log in, to log out, to deposit, withdraw, and transfer funds. And you should keep in mind, young one, that we may wish to add other use cases later. For example, the payment of utility bills. So then, my young novice, how would you architect the structure of the automated teller machine around its use cases?
You taught me that I should create interactors for each, Master.
Excellent, Grasshopper. You have created interactors around the use cases. You have interactors for logging in, for depositing, withdrawing, and all of the other use cases we mentioned. But now, young one, how will you communicate with the user? How will you ask the user to enter their PIN, or for the amount to enter for a deposit, or for which account to deposit into?
Master, I would add a display screen.
Grasshopper, Grasshopper, how many times must we tell you that the interactors should not know about the user interface? Do you not recall the lessons we taught you about boundaries?
I apologize, Master. I do remember about boundaries. Is this one correct?
That is acceptable, Grasshopper. You have created an interface named Messenger. But now, Grasshopper, tell me, what methods will you place in this interface?
Master, the messenger could have a method that allows the message to be delivered to the user.
Ah, Grasshopper, but if the method contains a string, does that not mean that the interactor must format that string? Tell me, young one, what principle does that violate?
The single responsibility principle, Master.
Hi, I'm Uncle Bob, and this is Clean Code.
I am Amanda. Hi, I'm Samantha. Hi, I'm Alexis. Hi, I'm Luna. Welcome to another episode of
Clean Code.
Clean Code. Clean Code. Clean Code. Your past episode is to begin a journey in this episode by Uncle Bob. Uncle Bob. Enjoy. Uncle Bob.
Welcome to episode 12, the interface segregation principle. Come on in. Let me take your hat. This is the 5th episode in our series on the solid principles. Remember last time we studied, after the wave-particle duality, we studied the principle that governs inheritance, polymorphism, and subtyping. Pretty good. We spent a little bit of time doing a quick tour through the mathematical theory of types and how those theories apply to computer science. We talked about subtypes, and we learned about Barbara Liskop's critical insight into their definition. We learned why that definition was important and studied its implications for static and dynamically typed languages. And then we dove into the wonderful old square rectangle paradox. And we found out what can happen when you ignore the principle of representatives. Remember, representatives don't share the relationships of the things they represent. Then we took a look at some heuristics, examples, and rules that helped us identify and correct violations of the Liskov substitution principle. In particular, we learned that derived classes should never do less than their base classes. Otherwise, there's a refused bequest. And then after that, in the context of a larger case study, we saw the kind of damage and pain and 2 a.m. prank phone calls that can be caused by violations of the Liskov substitution principle. Now in this episode, after we talk about the uncertainty principle, we're going to spend some time talking about one of the most foundational of all software design principles. A principle that says, don't depend on things you don't need. the interface segregation principle. We're going to talk about interfaces. We'll discuss where they come from, why they exist, and then we're going to talk about fat classes and the kind of damage they cause and the ways in which we can address that damage. Next, we're going to take a look at the definitive example for the interface segregation principle, the automated teller machine example. And we'll show the bizarre backwards force that violations of this principle can exert on elements of our architecture. After that, we're going to look at physical structure and pragmatics and show how we can arrange the elements of our architecture to balance those forces. And then finally, we'll talk about the true motivation behind this principle and the implications it has for dynamically typed languages like Ruby and Python. So strap the kids in the car, pile on in, and get ready, because we're about to drive headlong in to the interface segregation principle. In the last episode, I showed you this lovely interference pattern created when waves of light pass through the tiny slits in this diffraction grating. And I made the point that although you couldn't know where each individual photon was going to land, you did know the odds, because the odds of a photon landing are highest where the peaks of the interference pattern are highest. And so, in short, I said that the interference pattern was a pattern of probabilities. And then the light waves that made up the interference pattern were themselves waves of probabilities. If you want to know where a photon will deposit its energy, the best you can do is get the probability. And that's what this function does. This is the Schrödinger wave function. The value of this function at a particular location is the probability that the photon will deposit its energy at that location. And that, of course, means that the position of the photon is indeterminate. It is impossible to know where the photon is precisely because the photon has no precise position until it deposits its energy. Oh, we know something about the position of that photon. Within limits, we can define the path that it'll follow. But until that photon deposits its energy, it has no precisely defined position. This uncertainty was described by Werner Heisenberg in 1927. He used this simple expression: the uncertainty in position times the uncertainty in momentum will always be greater than or equal to half of Planck's constant. To say this more simply, you cannot simultaneously know the position and momentum of a particle. The more accurately you know one, the less accurately you know the other. The reason for this uncertainty is often related to the observer effect. The act of measuring the position of a particle disturbs its momentum. It's easy to understand this. In order to measure the position or momentum of a particle, you simply bounce another particle off of it. Of course, that changes the position and momentum of the original particle. By the same token, if I want to measure the position or the momentum of a particle, say this apple, I've got to bounce things off of it like these photons. And that changes the position and the momentum of the thing I'm trying to measure. Whoa! This explanation gives us hope that by improving our measurement technology, we can improve the accuracy of both position and momentum. And this is true to a point. But look at this equation again. It's got a hard limit. And the reason for that hard limit is that all particles are subject to the same probability waves that photons are. You might think that the atoms in your body have precise positions. But that's not quite true. The atoms within your body are made up of particles, protons, electrons, and neutrons. And the protons and neutrons are themselves made up of particles called quarks. All of these particles travel in waves. They all have a wave function. The probability that one of these particles will make itself felt at a particular location is the value of the wave function of that particle at that location. This might give you hope that you can force the value of the wave function to 100% and thereby precisely define the position of the photon. So let's try this. Get yourself a rope, sort of like this one, and we're going to take this in and we're going to tie it to the end of a doorknob. And we'll pull it nice and tight. We'll start to wave it around until we can get a nice standing wave. There we go. That's a nice standing wave. Nice bimodal standing wave. We can measure the momentum of that wave accurately. We know the frequency, we know the amplitude, we know the mass of the rope. So we can determine the momentum to arbitrary accuracy. But where is that momentum? It's everywhere on the rope. The momentum has no precise position. It's not just that we're uncertain about it. There is no position. It's utterly indeterminate. The momentum has no position. Now let's shake that rope one more time. But this time, we're going to shake it randomly. We're going to shake it with every possible frequency and amplitude. We're going to use perfect randomness, absolute white noise. Now look at that rope. It's dead flat. Why? Because the random noise integrates out to zero. For every wave in the up direction, there's a wave in the down direction. It all cancels itself out and leaves the rope dead flat. The position of that random momentum is clearly known. It's right there at the end of the rope where my hand is shaking like crazy. But that momentum has no value. It's purely random. It's absolutely indeterminate. What causes this indeterminacy? Waves. Waves. The momentum of a wave can be precisely known, but only if that momentum is everywhere on the wave. The position of the momentum can be precisely known, but only if the momentum is so random that it integrates out. The uncertainty principle is a principle about waves. Some people are bothered by the uncertainty principle because they feel that it limits their ability to know precisely what's going on. But that's just silly. I mean, you're not limited because you don't know the precise position of an ocean wave. An ocean wave has no precise position. That's not a limit. That's just reality. It is not the uncertainty of waves that people find so disconcerting. Rather, it is the fact that matter itself is made up of waves of probability. Long ago, in a galaxy far, far away, I spent a great deal of time debating object-oriented design in a news group called Comp.Object. The problem we chose was absurdly simple. Given a switch and a light, design the software that will turn on the light when the switch is activated. That's all. The debates raged for months. Some people wanted electricity to be an object in this design. Other people wanted the bulb or the base or the electric cord to be objects in this design. But we don't need to worry about such silly solutions. The simplest solution to this problem might be to have the switch object send the turn on message directly to the light object. Now, what don't we like about this solution? Let's look at the code implied by this diagram. First, we'll look at the switch class. Notice that the switch class contains the name light in the code. That's bad. I mean, a switch ought to be able to control a fan or a motor, not just a light. Why should the switch know anything at all about the light? Of course, this is pretty easy to fix. All we need to do is insert an interface in between the switch and the light. The interface will have the turn-on method. The light will implement the interface, and the light will supply the implementation for the turn-on method. But what should we name that interface? Believe it or not, in the 880s, we would have named that interface Abstract Light. I know that sounds ridiculous, but in the early days of OO, we thought that inheritance hierarchies should be named together and grouped together. In those days, we would have shipped light and abstract light together in the same component. In hindsight, of course, this was pretty naive. But it made sense to us at the time. You see, we knew that inheritance was a very strong physical relationship. And so we assumed that things that were physically strongly coupled ought to be shipped together. And so we would take whole inheritance hierarchies and package them together simply because they had this strong physical coupling. And since they're packaged together, they're named together. Thus, Abstract Light. And so it was only in the 90s that we began to understand the dilemma common to all statically typed object-oriented languages. That is, that inheritance, while it is the strongest of the physical couplings, is the weakest of the logical couplings. It's the switch that has the tight logical coupling to the interface. The switch can't do its job without that interface. On the other hand, the light considers the interface to be a nuisance. It doesn't care about the interface, it's just forced to drag it around against its will. And then the interface, it doesn't even know that the light exists. The tight logical coupling between the switch and the interface tells us that the two cannot be separated, and therefore they must be packaged together. Whereas the loose logical coupling between the interface and the light implies that they should not be packaged together, despite the tightness of the physical coupling. Indeed, if we take the switch and the interface and we package them together into a component, like a jar file or a DLL or a gem, and then we take the light and we package it into a different component, then we can deploy those two components separately. The light component becomes a plug-in to the switch component. In fact, we could create other classes like TV, blender, fan, have them implement this interface, and then plug them into the switch as well. So it's clear that the interface belongs to the switch. But what should we name that interface? Clearly, Abstract Light is the wrong name. So, some people like the name device. But I don't think that name works. Because it doesn't really tell you what the interface is about, right? So I picked out a few names here. Like turn-onable. That tells you what this interface is all about, right? You turn things on with it. Don't get that wrong now. Or activatable. That's kind of like what this interface does. Or switchable. That's pretty good, isn't it? Switchable. I kind of like that. Now, let's go with switchable. Notice how that name reflects the tight logical binding with the switch. This is typical for interfaces, because the name of an interface has more to do with its users than with its implementers. So let me repeat that, because this is an important principle. Interfaces have more to do with the classes that use them than with the classes that implement them. So what is an interface? Well, an interface is nothing more than an abstract class with nothing but abstract methods in it. So why do we need a special syntax element for that? In C++, for example, you could create an abstract base class with nothing but abstract methods in it. We didn't need some special kind of syntax for that. So why then, in C# and in Java, do we have this special syntax element with its own special grammar? What's that for? The answer to that question is both simple and depressing. The reason we have interfaces in these languages is that the language designers were too lazy to figure out a reasonable solution for multiple inheritance. In short, they punted. Regrettable. There are times when multiple inheritance can be quite useful. Now, in Java and C#, you can multiply inherit interfaces, but you can't multiply inherit classes. In those languages, you can only have one base class. The reason for this is so that the language implementers could avoid the so-called deadly diamond of death. The deadly diamond of death involves some ambiguities, which I can show you here with this example. We've got a base class named B, and that base class has an instance variable named V. There are two derivatives, D1 and D2, that add nothing. And then there's that interesting derivative M. M multiply inherits from D1 and D2, completing the deadly diamond of death. Now, the interesting question here is that within M, how many instances of the variable V are there? And there's two possibilities. In the one case, you might say that M derives from B, and since B has one V variable in it, M should have one V variable in it. On the other hand, you could also say that M derives from both D1 and D2, and therefore M should have a D1 object inside it and a D2 object inside it, which of course would give it two instances of the variable V. The problem is not impossible to deal with. In fact, it's rather simple. One could simply disallow the formation of the diamond altogether, or better yet, one could disallow simply variables in the apex of the diamond. Unfortunately, the designers of our languages took the easy way out and left us with crippled languages. We'll find out just how much that crippling cost us in a future episode. For now, we can look forward to Ruby, which solves the problem in an elegant and useful way. Have you ever wondered about the profitability of high-end photocopier companies? How do they make their money? One of their largest sources of revenue is in the selling of toner, the powdery substance that acts as their ink. This substance is generally made of the same substance as smoke, the black, greasy substance that accumulates on a plate held over a candle flame. And so these companies are very sophisticated organizations who manufacture highly complex machinery for the purpose of selling soot. Some years back, I was a software consultant working for such a company. we were working on a copier. The application code for the copier was all written in C++. It ran inside of a Motorola 68000 chip, and the clock rate was about a megahertz. That C++ software controlled every aspect of that machine. From the motors that drove the paper through the feeder, to the clutches that engaged the rollers that drove the paper through the paper path. From the sensors that detected the position of the paper, to the sensors that detected the phase of the photoreceptor belt. That software controlled the stapler and the stacker and the feeder and the page inverter, and it was also responsible for sending bits to the laser that transferred the image onto the electrostatic photoreceptor belt. In short, this software had a lot to do. The copier sat on a network. It was a network server. Users on the network would send it jobs, and the jobs would sit in a queue and would be executed in sequence. In order to execute a job, we had to schedule all of the operations inside it. This turned out to be a fantastically complicated affair. We had to know exactly when everything was supposed to happen. We had to figure out when all the sheets would move through the machine and where they'd be at which time. We had to know the precise millisecond at which to engage the clutch that would feed a sheet into the photoreceptor. And we had to know exactly what millisecond to tell the stapler when to staple a bundle of sheets together. So every motor, every clutch, every solenoid, every sensor, every actuator had a schedule for the whole job. And it was the master scheduler's purpose to tell every component when they were supposed to do their work for the whole job. As you might imagine, one of the major classes in this application was the job class. The job class gathered together all of the information about the job and supported all of the individual scheduling items in making their schedules. Because of this, all the major subsystems in the copier needed to know about the job class, and that gave the job class a huge fan-in, like this. Look at how those subsystems depend upon job, and they all depend on job for different reasons. For example, the stapler would go to the job class to find out how many sheets it had to staple and what the weight of the paper was. The imaging laser would go to the job class to find out the bitmaps of the images that it had to render. And the inverter would go to the job class to figure out which pages were double-sided and which ones weren't. In fact, the amount of information needed by these subsystems was enormous. So there were hundreds of different methods in the job class that were used by these subsystems. Now, this was a C++ project under active development in the early 90s. And one thing about a C++ project in the early 90s, compile times tended to be long. Indeed. The compile time of a C++ application depends on the number of #include statements that must be executed by the compiler. For those of you who are unaware of what a #include statement is, it's roughly equivalent to an import in Java or a using in C#. In C++, whenever a module is changed, then any other module that #includes that module has to be recompiled. The more modules that need recompilation, the longer the build time. So that copier application was a big C++ program, and it took a long time to build. If we had to rebuild everything, we could spend an hour or more at that. So you can imagine that we tried to avoid any change that would force a big rebuild. But now think about that job class and the huge fan-in that it had. That meant that even the tiniest little change to job forced a big recompile. And that took a very long time. And the unfortunate part of that is that that job class had a lot of reasons to change. So we were thrashing and rebuilding that system a lot, and it was painful. The developer in charge of the job class came to me in order to solve this problem. He needed a way to make changes to the job class without incurring these hour-long rebuilds. So we took a look at the problem, and as we pondered it, we noticed something interesting. The subsystems that depended on the job class all depended on it for different reasons. The number of methods they called was different. The methods themselves were different. They almost all called different methods. The overlap was actually very small. And that gave us an idea. Multiple inheritance was a brand new feature in C++ during those days, and nobody really quite knew what to do with it. But this looked like an interesting excuse to play with it. What if we were to create a whole bunch of pure abstract base classes? We call them interfaces today. And what if we put in those interfaces just the methods that certain subsystems wanted to call? So we'd have one base class, one interface per subsystem. And then, what if we had the job class multiply inherit from all of them? If we did that, then whenever you added a new method to the job class or changed an old method in the job class, the only subsystems that would need to be recompiled and rebuilt would be those that actually called those changed methods. The others would remain unaffected. Now, it only takes a minute or two to rebuild a subsystem, which means that changes to the job class could be made in a minute or two, not the hour that it took before. Oh, yes, we should try that. And when we tried it, we discovered that humans are strange beings indeed. There were several dozen different subsystems that used that job class, and that meant, of course, that we needed several dozen different interfaces to multiply inherit into job. But the compiler writers back in those days had never imagined that any class would need more than 8 base classes, so they limited multiple inheritance to 8. The compiler completely choked on our solution. We actually had to work around this by creating 2 tiers of interfaces that distributed the methods out to the subsystems. But it worked like a charm. Once that change was made, the build time shrank considerably. We stopped worrying about hour-long builds and started changing the job class whenever we felt like it. This was the first time I had seen the interface segregation principle used. I didn't even have it named by that point. But the idea was such a cool trick, and the effects were so positive to the architecture that I kept it around as a standard technique for years. It was only much later that this idea became the I in Solid. The problem that this principle addresses is the problem of fat classes. Classes that have lots and lots of methods. Job had a lot of methods because it had a lot of subsystems, and those subsystems had to manage a lot of data. There was no way to split the job class up because all that data had to be managed in one place, which meant that the job class had this enormous fan-in, lots of things depending on it, and that created a major bottleneck for the development of this project. Today's computers are an awful lot faster than they were back in those days, and that means that even in C++, build times aren't as much as an issue as they used to be. In Java and C#, build times are almost no issue at all, and that might make you think that the problem of fat classes has gone away. But no, it hasn't gone away, because fat classes cause another problem. The coupling involved with fat classes can be so severe that it can make it very difficult to take the clients and put them into separate components, like DLLs or jar files, and then independently deploy them. So, when faced with a fat class, we isolate that fat class from its clients by creating interfaces that those clients can use. Since interfaces are more logically coupled to the clients that call them than to the classes that implement them, we make sure that those interfaces contain only the methods that the clients wish to call, and then we multiply inherit those interfaces into the original fact class. By doing this, changes made to the function signatures of certain clients will not cause the other clients to change. This prevents them from being recompiled and redeployed. And that means that we can place those clients into separate components, DLLs, jar files, or gem files, and deploy them separately. When components can be deployed separately, that means they can also be developed separately, and that keeps the development teams from interfering with each other and stepping all over each other's work. Tell me, young one, what principle does that violate?
The single responsibility principle, Master.
Correct. The interactors control the use cases, and as we learned back in episode 9, they should not also be responsible for formatting the strings. Now then, young one, tell me, what methods will you place in that messenger interface?
Master, will these do?
Yes, Grasshopper, yes. The methods in the interface correspond to the messages we wish to display upon the screen, and some of those methods will have arguments, such as balance. Many will not. But now, my young one, let us say that we wish to use our automated telemachine in different countries where they speak different languages, such as Spain, China, or France. How will you handle this new requirement?
I would put the languages into subclasses, Master.
Of course, you know your lessons well. We would use polymorphic dispatch. Now, tell me, young one, which principles have we used?
Master, I have used both the open-closed principle and the Liskov substitution principle.
Oh, well done. Correct again, Grasshopper. Correct again. It warms my heart to see you learn so well. But now, youngster, there's a problem. A deep and dangerous problem. Have you seen it? Do you know what it is? Can you tell me why this system would be hard to maintain?
No, Master, I do not understand. I have used all the principles you have taught me. Why should the system be hard to maintain?
It is because, young Grasshopper, you have more principles to learn. Consider, your customer comes to you and tells you that they wish to add a step to the withdrawal use case. After the user has entered the account and the amount, you are to put up a message on the screen informing the user that the bank is going to be charging them a service fee, and they want the user's approval. How will you change the design now, youngster?
Master, I would add the request approval of fee method to the messenger.
Silly six-legged fool, do you not see what you have done? Imagine that your language is Java or C# or even C++, and now you have added a new method to the messenger interface. Tell me, what classes will be affected by this change?
Master, all interactors must be recompiled and redeployed.
And what principle does this violate, young locust?
Master, it violated the open-closed principle.
Indeed it does, Leaf Chomper, indeed it does. A change to the withdrawal interactor has forced you to add a method to the messenger interface, and that forces you to recompile and redeploy all the other interactors. Would this not make the system rigid, little bug?
Master, it would.
And fragile?
Yes, Master, and fragile.
And what would your customers and managers think of you if you gave them such a system?
Master, they would think I had lost control of my software and did not know what the hell I was doing.
And so they would, Grasshopper, and so they should. But I can see by your face, youngster, that you have a question Ask it, my flittering young flyer, ask it.
Master, we changed the withdraw interactor, and yet all the other interactors were affected.
That is true, my hard-shelled novice. Why does this confuse you?
Because, Master, all those other interactors do not depend on the withdraw interactor.
Hi-ya! Ah, you are observant, young student. Ask your questions.
Master, how can a change to a module affect other modules that don't depend on it?
That is the correct question, young master. And since you have asked so astute a question, I will answer you quite directly. What you have noticed is the strange reverse dependency that occurs when a class knows too much.
Which of my classes knows too much, Master?
All the interactors, Grasshopper, all the interactors. Do they not all depend upon methods that they never use? Does not the withdrawal interactor depend upon the ask for card and ask for pin methods in the messenger?
Yes, Master, it does.
And does it need to, young hexapod?
No, Master, it doesn't.
And when the request approval for fee method was added to the withdrawal interactor, did not all the other interactors depend upon that method? Yeah.
Yes, Master, they did.
Did they need to, Grasshopper?
No, Master, they didn't.
Look with those multifaceted eyes of yours, oh young one. Do you see the strange backwards dependency that couples all of the interactors together? Can you explain it?
Yes, Master, I see it. Each interactor depends on methods that it does not need, but that are needed by others.
So then, my exoskeleton apprentice, how shall we solve this problem?
Master, we must prevent the interactors from depending on methods that they do not call.
Yes, Grasshopper. And how should you do that?
Master, I must move the methods into separate classes, one class for each interactor.
What will you call those classes, young one?
I would call them login messenger, withdraw messenger, deposit messenger, and transfer messenger, Master.
And which methods will you put in each, my little blade jumper?
Master, in the login messenger, I would put only those methods needed by the login interactor, and the same for all the other messengers.
But Grasshopper, what of those 3 languages we must present to our users? Are you going to create 3 new derivatives for each of those messengers?
Master, I fear that would be too many classes.
I agree, my little dew-jumper. So now, what will you do?
Master, I do not know what to do now.
Then watch and learn, little boot-biter. We can turn all of your messenger classes into interfaces, and then we can multiply inherit all of those interfaces into your original messenger interface. And from there we can derive the 3 language subclasses. Do you understand now, Grasshopper?
Yes, Master, I do.
Is the strange reverse dependency broken?
Yes, Master. None of the interactors depend on methods that they do not need.
And when one interactor needs a new message, will the other interactors be affected?
No, Master. They won't need to be recompiled or redeployed.
Return to your exercises, young one. We've done enough of this for today. So that was kind of cool, wasn't it? That weird backwards coupling that comes from too much knowledge. So the goal of the interface segregation principle is to prevent that backwards coupling by ensuring that you don't depend on methods that you don't call. Indeed, we can generalize this principle to say simply, don't depend on things you don't need. Otherwise, you'll create couplings that will make your software rigid and fragile. And you know what that means, don't you? Or do I need to say it again? So let's return to the ATM example, and let's assume that the implementation language is Java. We've got this messenger interface, and it contains all of the methods that correspond to all of the messages that can be displayed on the screen. Let's also say that we've segregated the login messenger, the deposit messenger, and the withdrawal messenger. Let's also assume that there's a common messenger interface that contains all the messages that are commonly used by most, if not all, of the interactors. This means that each of the interactors is going to have to know about two messenger interfaces, the one that's designed for it, and the common messenger. So, the constructor of, say, the withdraw interactor should look like this. But wait, those two constructor arguments are being passed the same value. Look at how that constructor is called. Both those arguments are passed the instance of the messenger. So, maybe we should just pass one argument into that constructor. But if we do that, what type should that argument be? We could make the type of that argument the messenger class, the class that inherits from all the segregated interfaces. But if we did that, we'd simply have the reverse coupling problem again. So, then we can't do that. So let's go back and look at that two-argument constructor call again. You see anything wrong with that? Why should the code that calls the constructor know about the messenger instance? What right does it have to that knowledge? That's knowledge we'd actually like to keep away from the rest of the system because that messenger instance implements all of these segregated interfaces, and we don't want the rest of the system to take advantage of that knowledge. After all, at some later date, we might decide that those segregated interfaces should actually have separate implementations. And we certainly don't want the rest of the application to know about that. So then, it's perfectly clear that that constructor should have two arguments. The question is, how can you call that constructor without knowing that both arguments are implemented by the same messenger instance? Remember the boundary that separates main from the application? We talked about this back in episode 3. Since the messenger instance is going to be created on the main side, it's okay if all the interactors are created on the main side too. After all, if main is going to create the messenger instance, well then it already knows that that messenger instance implements all of the segregated interfaces. So there's no point in hiding that from main. We do want to hide it from the application side of the boundary. So main could simply create all the interactors and pass them across the boundary without leaking any of that knowledge. So another slightly more complicated way of doing this would be for the application to create the interactors, but without any of the messenger interfaces set. And then the application could pass all those interactors across the boundary into main using the builder interface. Over in main, the builder could use an array of setter methods to set the messenger interfaces on the interactors. Clever, isn't it? What about a messenger factory that had getter methods for each of the segregated interfaces? You think that might be a good idea? That factory would simply return the messenger instance through each of the getters. And that would keep the application side from knowing that the segregated interfaces all had a common implementation. However, that factory interface is something of a dependency magnet. Now imagine a module that depends on one of the segregated interfaces. In order to get an instance, it's going to have to go to the factory. But the factory depends on all the segregated interfaces. So every module that depends on at least one segregated interface will actually depend on all of them through the factory. So that factory could cause that strange reverse coupling to get asserted again. Any change to any one of the segregated interfaces could force the messenger factory and all of its clients to be recompiled and redeployed. Another solution might be for main to create the instance of the messenger and then hide that instance behind a static variable of type object or a static getter method that returns object. Then the interactors could simply get that object and cast it to the segregated message type that they need. This works, but there's a hidden implication. The fact that the application must cast the object to the interface implies that the object implements more than just that interface. And that's exactly the knowledge we were trying to hide from the application. You know what? I just had a thought. We could use dependency injection to inject those interfaces into our application. Yeah, that sounds like a great idea, huh? I mean, dependency injection is cool, right? Actually, yeah. Dependency injection is cool. With one great big exception. I don't want the application to know that it's being injected into. Or to say this a different way, I don't want anything on the application side of the boundary to depend on any aspect of the dependency injection framework. The last thing I want to see is a whole bunch of dependency injection annotations littering up the code on the application side of the boundary. I don't want anything on the application side of the boundary to call any service locators or any other dependency injection framework functions. I don't want the application side to know anything at all about the implementation we've chosen for injecting dependencies. That kind of knowledge belongs on the main side of the boundary. I'm perfectly happy to inject dependencies into main. And that leads us right back to our original solution. It's main that should create the messenger instance. It's main that should create all of the interactors. And then main should take those interactors and pass them across the boundary into the application. On the surface of it, the interface segregation principle seems to be about static typing. The putative proof of this is that in dynamically typed languages like Python or Ruby, the strange reverse dependencies experienced by Java or C# simply don't exist. Imagine the ATM example written in Ruby. The messenger instance would contain all the methods for every message that could be displayed. But the interactors would only depend on the methods that they actually called. They have no knowledge at all of the other methods in that messenger. Because no interface exists in Python or Ruby, no abstract class needs to be created. Interfaces in dynamic languages are infinitely segregated. So does that mean the principle doesn't apply to Ruby or Python? Oh, it applies all right. It certainly does. Just not in the glaring way that it applies to Java or C# or C++. It applies because the interface segregation principle really says, don't depend on things you don't need. For example, have you ever had to create an instance of an object and pass in constructor arguments that you have no use for? You found yourself depending on something that you don't need simply to satisfy someone else's need. Have you ever had to build up a complex data structure simply in order to run a test? Or have you ever had to fire up the web server and connect to the database just to test a simple concerned business rule? Have you ever had to load a gem, a jar, or a DLL file simply to satisfy some part of a library you weren't going to use? Have you ever been forced to write a test that walks through the login process simply so that you can then test a business rule? Was there ever a time, my friend, when you wanted to call a function, and yet in order to call that function you had to call two other functions first, and you didn't know or care what they did? All of these are violations of the interface segregation principle, because all of them result from designs that leak their abstractions all over their users and force them to depend upon things they don't need. It is the ultimate arrogance of library designers that they force you to use strong physical couplings like inheritance. They ask you to derive from their base classes, or they ask you to create instances of their concrete classes. They force ugly dependencies upon you. They violate the interface segregation principle by foisting their needs upon you. So here is the final nugget of truth you need to take away from this lesson. The grand stroke of knowledge that needs to be embedded into your mind. Don't force your users to depend on things they don't need, whether those users are modules, people, or tasks. Don't force them to know more than they need to know. And that's really the bottom line here. The interface segregation principle is all about the need to know. Loose lips sink ships, and leaky abstractions create distractions. Keep your abstractions private. Dispense knowledge only to those with a need to know. Play your cards close to your chest. And be wary of systems that blab too much about private details. Oh. So, there you have it. That's the interface segregation principle. Fun, huh? Oh. Ah. We looked at interfaces, why they exist, and what to name them. So then, we talked about the problem of fat classes. And we discussed the damage they can cause and how to fix them. Next, we studied the automated teller machine example, and we saw the strange backwards force that happens when you violate the interface segregation principle. We took a close look at the pragmatics and physical structure behind the interface segregation principle. And we noted once again the importance of that boundary that separates main from the rest of the application. Finally, I told you the true motivation behind the interface segregation principle and how it applies to dynamically typed languages like Ruby. Remember, loose lips and leaky abstractions sink software. So after this long journey through code, design, architecture, and interfaces, we've come to the end of episode 12. But boy, we've got a lot more to talk about. There's still one solid principle left, And then after that, we've got the component principles, we've got design patterns, advanced test-driven development, agile practices. You're not going to want to miss the next exciting episode of Clean Code, episode 13, the dependency inversion principle. Come on, you dogs. Let's get going. We got to go take a look at this house. See how they're doing with it. Come on, you dogs. Good dog. Good job. In this diffraction grading. And I made the point that all you gentlemen out there are damn fools.
Nice.
Goodness. This uncertainty was described by Vernon Heisenberg. Vernon. Whoa, Vernon Heisenberg. Hey, man. How you doing? Hey, Vern. Now let's shake that rope one more time. But this time we're going to shape it. We're going to shape it into a heart and send it to our little Valentines. The more, the longer the build time. The build. Ah, you are observant, young student. Listen to the bells dingle and dingle. Isn't it nice? The angels have rewarded you. But wait. Okay, I'm done waiting now. Next, we studied the automated teller machine example. And we saw the strange backward force that occurs when you eviscerate the interface segregation principle. Remember, loose lips and leaky abstractions sink ships. No, software. Between the interface and the light suggests that they should not be packaged together, despite the fact that dogs are barking in my spaceship. Why are there dogs barking in my spaceship, Captain?
That door is open.
Captain! Captain, I hear dogs barking. This is highly irregular. We shall now wait for the dogs to stop barking. Space dogs are attacking the ship.
We're under attack. Shields! Who needs shields?